passar agora a palavra para o nosso primeiro palestrante, que é o professor Björn Kjerfve. O professor Björn é um matemático, oceanógrafo, tem uma longa história de cooperação com o Brasil, vários talvez aqui no auditório conheçam. Cooperou durante muitos anos com a FURG, com a USP, com a UF em Niterói, e hoje é presidente da Universidade Marítima Internacional, da Organização Marítima Internacional das Nações Unidas, que é uma universidade que se dedica à formação em nível de pós-graduação na área marítima, incluindo principalmente logística, comércio internacional, impactos de mudanças globais. E hoje o professor Björn, como oceanógrafo que é, vai dar uma palestra científica. E amanhã vai participar também do nosso debate, já que o Brasil tem um grande interesse em participar da Universidade Marítima Internacional, que é uma necessidade nossa. Hoje, 90% do PIB brasileiro é escoado através dos oceanos, e acho que está mais do que na hora de a gente ter uma universidade também dedicada a esse assunto. Então, o professor Björn vai fazer uma conferência sobre Changing Oceans and Coasts, Contemporary Issues. Em princípio, o professor Björn tem de 30 a 40 minutos, mas como nós vamos ter uma conferência faltando, a gente fica com o tempo um pouco mais livre. Então, professor Björn, por favor.
Good morning, everyone. Thank you for the opportunity and the honor to be here to address you. Before I decided to give this presentation, I thought, should I try to do that in Portuguese? That would be pretty poor. I could give it in Swedish, of course, but I don't think you would understand. So we are therefore compromising, and I take the opportunity to give the presentation in English. The oceans make our planet the only blue planet in our solar system. And this is quite important because water sustains life the way we know it, and the incredible latent heat characteristics of water buffers our climate. Oceans started forming some 4.5 billion years ago, shortly after the formation of Earth. And still we don't really know where the oceans came from. The hypotheses range from degassing of water from rocks or from capture of ice particles from space. Today, however, 71% of the ocean surface is covered with ocean water, on average 4.8 kilometers deep, and 96.5% of the water is water by weight, whereas 3.5% are dissolved minerals, mostly sodium and table salt. And the interesting thing, of course, is the oceans are slowly but systematically getting saltier with time. Despite the abundance of ocean water, potable water on our continents is very scarce. But that is largely a function of human demographics on one hand and local climate on the other hand. And most important, life as we know it has evolved because of the oceans. As human beings with a short lifespan relative to geologic time, we have a tendency to want things to stay the same, that we have known them always. We want things to be constant. But that's not the way life is. Things are changing. They are changing all the time. And change certainly is taking place in the oceans and coastal areas of Earth. For at least the past 40 years, since the early 1970s, we have posed a hypothesis that anthropogenic change, impact of human, is in fact responsible either wholly or in part to observed ocean change. This is quite a plausible hypothesis if you consider the very explosive growth of the human population. In 1800, the global population was about 1 billion. Then it increased to 1.8 billion by 1900. In 1968, it was 3.5 billion. That's in your lifetime. And today, only 44 years later, the human population has doubled to today exceed 7 billion persons on this planet. And predictions are, and they're very widely, depending on the assumptions that you make, that human population will be anywhere from 8 to 10 billion persons by 2040. Of course, that could be too little. So the so-called greenhouse warming is a principle and effect of the ever-increasing concentration of carbon dioxide in the atmosphere as a result of the industrial revolution, that is burning of fossil fuels since approximately the beginning of the 19th century. By 1750 to 1800 approximately, we know that the atmospheric carbon dioxide concentration was at around 280 parts per million by volume in the atmosphere. But by 1958, it had increased, we know, to 350 parts per million. And 1958 is a very important year with respect to carbon dioxide in the atmosphere, because that was when David Keeling of Scripps Institute in California started measuring carbon dioxide from Mauna Loa in Hawaii, demonstrating with this fantastic time series of his that carbon dioxide is like human population, increasing exponentially, today measuring more than 392 parts per million. Other greenhouse gases besides carbon dioxide are of course also responsible for the global warming, principally methane and nitrous oxide. So what's the coupling? We know that the shortwave radiation coming from the sun largely passes through the Earth's atmosphere. It heats the surface of the Earth, including the oceans, and then the oceans and the land re-radiate long-wave radiation to space, but a portion of this is actually being captured by the greenhouse gas molecules, carbon dioxide, methane, and nitrous oxide. There are quite a few opponents to this scenario. They are quite vociferous. We are also dealing with very complex processes, with complex and not very well understood feedback loops and non-linear effects. So those who oppose this scenario can certainly argue, and they do so vociferously. You know, there are a number of very marvelous technological advances which have occurred primarily during the past 40 years that makes it increasingly easier for us to observe, to monitor, and model ocean and coastal change. These technological advances have in fact revolutionized oceanography since 1970, 1972, and I will give you a few examples. The advance of satellites for civil purposes have been used to measure weather, including ocean weather, color of the oceans. They have surface temperature, estimating chlorophyll, measuring heights with altimeter, which can resolve both tides, waves, and water level change. And they do so in every better detail and with greater dynamic range. It's very impressive. In 1983, a very unfortunate event, flight KL Korean Airlines 007 was shot down on a flight from the United States to Seoul, South Korea. And this prompted the release or the commitment to release GPS as a navigation technology for civil use. In 1993, the United States had put into space a full constellation of 24 navigation satellites that were then fully operational. And then in 2000, on his last day in office, President Bill Clinton signed an executive order to make a non-degraded GPS signal available for all civilian use. Fantastic technology. And then came computers. Computer power has grown exponentially with silicon chips, solid-state memory, increasingly large hard drives, with doubling of computing power every 18 months. And now, with everything up in the clouds, can be sent there, stored there, with databases housed in the clouds. This has also allowed us to develop ever more complex 3D operational numerical models with forecasting capabilities, which allow us to see the ocean like never before, details of eddies, meanders, and how they connect globally. The visualization of ocean circulation, here shown by the NASA Jet Propulsion Laboratory ECHO 2 model, shows you the ocean circulation in incredibly rich detail. I can stare at this visualization forever, and every time I see it, I see something completely new. It is fantastic technology that I can't get enough of. It certainly is a great change if you remember those early textbooks like the famous The Oceans by Swerdrup, Johnson and Fleming. This is not the way ocean circulation looked in those books. Also, our ocean instrumentations has matured fantastically at an incredible rate. We now have Doppler current meters, buoys, ocean gliders, drones and other platforms and devices, all with embedded computers with the ability to monitor and recording change of ocean and coastal events in near real time. These observations are integrated with simulation modeling and satellite operations, and then uploaded by satellite and transmitted to laboratories and scientists, or alternately sent by fiber optical cable, as in the case of the incredibly richly instrumented Quantifuga platform of Vancouver Island, Canada, where this entire lithospheric plate has been instrumented with all kinds of instruments, and where observations of volcanic outbreak was actually captured, and the signal directly sent both to research laboratories and to classrooms around the world. This is the Neptune project that I'm talking about. And then the ongoing effort is to map ocean bathymetry and ocean resources in incredible detail using GPS technology and GIS mapping tools. That's ongoing, and it's one of the primary efforts today. But not only is it the equipment themselves that are incredible, it is also how we work with the equipment. And what we see today is that oceanography and the study of the oceans and the coast is being carried out by not individual scientists, but by teams of international scientists who collaborate across continents and using technology. And that has given rise to a number of global projects that are known by their acronyms: GEOSEX, OSI, IODP, JGOVS, and other studies. They all use ocean measurements, drilling results, trace elements, decays of radioisotopes, and numerical models to interpret ocean circulation, biogeochemical cycle, and Earth processes and cycles like never before. At the same time, there's a curse with technology. They also serve marine pirates well. Through the availability of this advanced technology, marine pirates off Somalia and in other places can select ship targets. They can carry out very advanced attacks on ships, and they can illegally seize ships, crew, and the cargo and sell it back for ransom. Of course, there's a loss of violence in between. Through the use of modern technology, we have also been able to understand the rate of change, which is very important. We always initially thought that global change took place in a slow and steady manner. We know better now. We know from the drilling course by the IODP JOIDES resolution that decadal scale global climate change has taken place in past geological time. And of course, Brazil is very much a partner in the IODP project. And we also know of instantaneous change that can happen, as in the case of the 2011 Tohoku 8.9 Richter scale earthquake that took place only 70 kilometers offshore of Japan, west of Japan, creating an incredible tsunami which in about a few minutes had made it inland, causing a tsunami wave as high as 10 meters in the inland areas of the coast. I viewed, together with many Europeans, this terrible disaster in real time on television early in the morning. Unfortunately, it resulted in a death toll of 16,000 persons, affected a swath of 2,000 kilometers of coast, and also was responsible for the near meltdown and the shutdown of 3 too close to the shore nuclear reactors, and then as a consequence altered Japan's policy on the use of nuclear power. The World Meteorological Organizations and UNEP established the Intergovernmental Panel on Climate Change in 1988 to assess which portion of change is induced by anthropogenic factors. The fourth assessment report, AR4, was published in 2007 and builds on 3 previous sets of assessment reports. And these reports are based on the participation, the analysis, and the modeling by more than several thousand scientists. And I think, in fact, there might be a few of you in the room who are participating in the IPCC effort. But this assessment report is critiqued very heavily by some skeptics and non-believers of global warming due to anthropogenic factors, at the same time that others think that the report, the 2007 report, is far too conservative in its estimates. You can't make everyone happy. Certainly, according to the IPCC, population growth, economic growth, energy systems, and more energy use, and the social development are all driving factors for climate change. Change, of course, is a mixture between naturally occurring change and that which is anthropogenically related. primarily through the burning of fossil fuels, with increase of carbon dioxide and other greenhouse gases in the atmosphere. The IPCC fourth assessment scenario has provided a model-based prediction based on a matrix of possible events, looking at a homogenized global distribution of population versus a more regional set of distributions, and also comparing economic and environmental factors to create a series of scenarios, primarily 4 basic scenarios with some variability. We know for a fact that change has taken place during the past century. It's very well documented. And we also know that change in many respects has accelerated in the past 1 to 2 decades. The average global surface temperature has increased by 1 degree Celsius since 1950. And we know it has also increased by 0.2 degrees Celsius in the past decade alone. Based on IPCC model scenarios, temperature is projected further to rise by anywhere from 1.8 to 4.0 degrees Celsius by 2100. And regions that are dry today are projected to get still drier, and regions that are wet today are projected to become still wetter. Sea level likewise has risen, and we know by 1.3 millimeter per year between 1961 and 1993. And since 1993 to the present, the absolute or eustatic sea level has risen by 3.1 millimeters per year. This increase in sea level, 58% of that is explained by thermal expansion. 28% from melting of glaciers and small ice caps, and 15% from polar ice sheets, mostly in the Arctic region, including Greenland. Ice and snow have melted at an average rate of 2.7% per decade since 1978. That's pretty alarming. As a result of global warming, the intensity of tropical storms, hurricanes and typhoons and the like, are observed to occur increasingly more frequently, the so-called super hurricanes. And they are likely to continue to do so. Heavy precipitation events are also likely to become more frequent, and therefore will increase floods and flood risks and impacts. According to the fourth assessment report of the IPCC, static sea level will rise anywhere between 18 and 59 centimeters by year 2100. That may not be so much, but it will clearly expose coasts to increased erosion. Many more millions of people are projected to be flooded every year by sea level rise, at the same time that hurricanes and typhoons will increase to continue, and they will cause change in a catastrophic way when it happens. Local relative sea level change may, of course, be much greater, but that would be variable across the globe. So let me turn to the IPCC fifth assessment report. The fifth assessment report will be published sometime late 2013, and like the others, it will be several volumes and will be continued to be published to 2014. And it's currently in review state. And there are remarkable revisions in that report to the expected rate of global sea level rise. In fact, the fifth assessment report will call for a 2-meter increase in eustatic sea level by 2100. The impact on human life and coastal system will obviously be enormous. if and when this happens. It may also be quite advantageous to look at eustatic sea level change against the backdrop of cycles of glaciation and sea level variability. And I am showing that here during the latter part of Quaternary, a very short time period of Earth history, less than the last 1 million years. There are many theories to this great variability in glaciation on the planet, and therefore sea level stand. But what can be noted here is that we are currently at a high sea level stand, and whatever anthropogenic change is happening relative to the high state. So, as you can see here, we have not previous in the Quaternary anyway had a higher sea level stand than the present. Sea level rise is certainly not going to be slow and steady. Our measurements indicated that it is, but when you get impact on the coast, it happens as a catastrophe. It's a catastrophic event, and it's associated with hurricane landings, riverbank overflows, and this image here is from the Hurricane Katrina in 2005, which made landfall in New Orleans in the United States and Louisiana. It flooded extensive portions of coastal Louisiana and all of the city in New Orleans. Was responsible for the death of some 9,000 individuals, unfortunately. And the only reason that New Orleans is again a city is because the U.S. Corps of Engineers managed to wrestle back New Orleans from the ocean by a combination of building levees, channelizing water flow, and pumping water. Some large cities, primarily in Delta region of the world, including certainly New Orleans, Bangkok, Houston, and others, are particularly threatened by sea level rise. Also, the disappearance of sandy beaches, something which was first noticed in the early 1970s, is a result of climate change, because of rising sea level. Sea level also will affect agriculture in low-lying coastal areas, and will therefore drastically affect millions and millions of people, and mostly in the poorest countries of the world. Also, the fact that there today are more than 2 million river dams, which all capture sediments that previously used to transport sediment or allow sediments to transport to the ocean, are now trapping the sediments, therefore stopping the sediment supply to the coast, with the consequence of further accelerated coastal erosion. And the IPC scenarios include all of these different processes. Well, I know that you cover from many different fields of oceanography, and I'm now going to venture out in the chemical area, which is the one that I struggle with the most. But we can say that oceans also play a major role in any climate change scenario for two reasons. One is this incredibly latent heat buffering effects of water. And the other one is that the ocean serves as storage to 80% of the global carbon dioxide concentration, far more than in the atmosphere. As oceans absorb carbon dioxide, they change ocean chemistry. It lowers pH. It reduces the carbonate ion concentration and lowers the saturation state of biological calcium carbonate minerals. These chemical changes are, in a unified way, referred to as acidification. But cold water stores more carbon dioxide than warmer water. And the upper ocean temperature is rising, and therefore it can be expected that for for the sake of this process alone, the oceans will further enrich the greenhouse gas concentration of carbon dioxide. But at the same time, the oceans absorb more carbon dioxide than it emits because of ocean life, phytoplankton and microbes, which depend on carbon dioxide in the oceans for their existence. And they in fact create a biological carbon pump that removes vast quantities of carbon dioxide from the atmosphere. So you see different processes work in different directions. But as a result of increased carbon dioxide concentration in the atmosphere, ocean acidification is taking place, but it's not really acidification per se. Of course, the oceans are having a pH value greater than 7. It is just a reduction of the pH of the oceans, a slight reduction of that. And we know that from about year 1800 to year 2000, the oceanic pH value decreased from approximately 8.2 to approximately 8.1. And this corresponds to an increase of 30% of the hydrogen ion in ocean concentration in ocean water. The IPCC forecast, and again with divergent opinions, is that ocean pH will decrease by 0.3 to 0.4 pH units by 2100, which corresponds to a 130% increase of the hydrogen ion concentration in ocean water compared to the concentration in pre-industrial times. Increasing surface ocean temperatures, which are observed, have resulted in massive coral bleaching across the globe. And bleaching is in fact a form of climate change on a whole ecosystem. But more important, increasing lower pH, or so-called increasing acidification, will impact the production of calcium carbonate shells, plates, and organic skeletons, that is, calcification, which is essential to the survival of many marine organisms. Calcification involves the precipitation of dissolved ions into solid calcium carbonate, structures such as coccoliths and corals. After they are formed, such structures are vulnerable to dissolution unless the surrounding seawater contains saturation concentrations of carbon ions. As a consequence, the world's coral reefs are at significant risk, both from increased ocean surface temperatures that cause bleaching and also from the future acidification process. The acidification issue is both a grave issue and a complex issue. It's expected that ocean acidification, i.e. the slight lowering of pH, will lead to a significant decrease in burial of carbonate sediments or even the dissolution of existing carbonate sediments. This will elevate ocean alkalinity and may also lead to the enhancement of the ocean as a reservoir of carbon dioxide, which will further enhance climate change. Marine debris. It's become a hot topic. 80% of ocean pollution is land-based. It comes out via rivers from the coast and seeps out into the ocean. But debris is found everywhere across the oceans on a very massive scale. Marine pollution and dumping at sea are regulated by the London Convention of 1972 and by MARPOL, an IMO Convention 1973 and 1978. Ocean debris consists of many different things. Plastics, cigarette filters, bottle caps, plastic bags, balloons, buoys, rope, medical waste, glass, plastic bottles, styrofoam, nets, six-pack rings, and nurdles. Nurdles are broken down plastic particles smaller than 5 millimeters. And incredibly also, 61,000 Nike sneakers. When the container vessel Hansa Carrier in 1990 ran into foul weather in the mid-Pacific and tilted and lost 21 40-foot TEU containers containing the Nike sneakers. The Nike sneakers were released, and an old office mate of mine at the University of Washington, Curtis Ebbesmeyer, made a fantastic scientific fortune out of this by using these Nike sneakers as a Lagrangian measure for many years afterwards. Mid-oceanic gyres, which are anticyclonically rotating water masses, serve to capture marine debris. This includes the Sargasso Sea in the North Atlantic Ocean and what's called the Great Pacific Garbage Patch in the North Pacific Ocean. As you know, when the first European invaders of the Americas started traveling across the Atlantic Ocean, they observed the tremendous collection of sargassum in the Sargasso Sea, giving the name to this particular portion. But with a cyclonic type of a circulation, it has a sense of bringing things from the perimeter in towards the middle, and the maintenance of these sargassum and also the nurdles and other plastic and other debris in these major ocean gyres is a function of the oceanography. We don't know how much garbage there is. We know that there is a lot, and although sampling is continued or gone on for maybe several decades already, there is now a renewed effort to emphasize this as a critical topic of research. We know that the Great Pacific Garbage Patch covers some 1,400,000 square kilometers. That's about 80% of the size of the Caribbean Sea. And this area contains an estimated of 1.5 million tons, metric tons, of plastics, which equals to 6 kilograms of plastic for every 1 kilogram of phytoplankton in the same area. Much plastic is non-biodegradable, and it never fully decomposes. That is, some people like to say it has an infinite half-life. It only breaks down into increasingly smaller particles, the so-called nurdles. Birds and animals, fish and turtles eat and are tangled in plastic debris. Marine microbes digest some of the plastics and may, in the process, actually leak some toxic additives into the food chain. Inventory of marine debris in the ocean is certainly needed, and this effort is currently underway. Debris is clearly a very emotional issue and needs to be dealt with analytically through analysis and action. Marine fish account for 20% of all animal protein in the human diet, and 1 billion people on Earth rely primarily on fish as their source of protein. Fish are thus important as food, and it's also fishing is an important factor in global employment. Current harvest trends and fishery conditions put both at risk. Overfishing results in depletion of fish stocks, low biological growth, and critically low biomass levels. Heavy commercial fishing pressure has led to overfishing and declining fish stocks, or at least threatened stocks, primarily with respect to desirable demersal fish or high-valued pelagic fish. The fishing has as a consequence shifted to smaller fish from greater depth and to new species. As a result, the global fish harvest is still increasing, but only so much, and it's being augmented by marine aquaculture. As a consequence of the heavy fishing, many fisheries have collapsed, or almost collapsed, such as the anchovy fishery of Peru, or the fishery in the Gulf of Thailand, which today is about 20% of what it used to be in 1960, in spite of more fishers, more fishing boats, a greater fishing effort, and smaller mesh sizes. On top of that, we have seen the building of super trawlers. The super trawlers are greater than 150 meters in length. They have flash freezing capabilities on board that can instantaneously freeze fish to minus 60 degrees Celsius on board. They have a capacity for holding up to 2,500 metric tons of catch. And these ships are becoming increasingly more common. But they have also been banned in Australian waters for the risk of eliminating certain local fisheries. Certain species are threatened. The bluefish tuna has escaped being placed on the endangered species list by NOAA in the United States, but is listed as a species of concern. At the same time, the EU, the European Union, is considering electronic monitoring of tuna catch quotas. And the Pew Foundation, in a statement, calls for full electronic boat-to-chopsticks surveillance of tuna. I like that. Certainly, the bluefin tuna fishery is non-sustainable, and adherence to global quotas is called for. Further, because of ballast water transport, adherence of animals and plants to ship hulls, and accidental intentional release of aquarium species, invasive species have become major problems in many ocean and coastal areas. The example here is what's referred to as the beautiful aquatic rat. It's a lionfish, indigenous to the Indo-Pacific, beautiful to look at, and this fish has in the past 4 years infested the Caribbean Sea, the Gulf of Mexico, and the eastern seaboard of the United States. They multiply fast, extend their range northward, and eat everything in their way. And there is no good solution to control this explosive growth. Maybe we need to start a fishery and do some overfishing. And then there's the case of what I call the frivolous fishing. This is as in the case of manta rays, these beautiful rays that exist globally. They are slaughtered in mass, in particular in India, Sri Lanka, the Philippines, and Mexico. And they are not slaughtered for their meat. They are slaughtered simply for its 10 gill rakers. These are cartilage features surrounding their gills. These are dried. They are used for Chinese medicines. They are used not because they work well, but because they are a product of marketing. They stand a chance of eliminating manta rays and other rays from the oceans. So, these are examples of how the oceans are changing as a result of humans. Adherence to catch limits, legislation, better fish management, as well as enforcement of international quotas and conventions are needed to regulate ocean fisheries. It's really interesting to note that wars can actually have a beneficial outcome. The threatened North Atlantic cod fish rebounded spectacularly after the Second World War, and for 6 years the fishing efforts in the North Atlantic was cut down severely. Likewise, tuna stocks, which have been exploited very, very heavily off the coast of Somalia, is suddenly rebounding in a fantastic way because of the prevalence of marine piracy in those waters. But nobody is catching the tuna, and that's the case. And I can also make a comment that the 2010 Deepwater Horizon accident of Louisiana did wonders for the rebound of several fish stocks in the Gulf of Mexico. And the fish catch in the past year grew by 50% as compared to the fish catch in 2010 before the Deepwater Horizon. Not only is it important to understand the processes associated with a change in natural ocean systems, but it's also important to understand how they're impacting global economics and how we adapt to change and take advantage of these opportunities. Global warming will have enormous impact on maritime trade and ocean resources exploitation in the Arctic in particular. In historical times, Arctic sea ice cover reached an absolute minimum in September 2012, when the ice cover was 40% less than 30 years ago. This composite satellite image from just 2 weeks ago was made on the 16th of September 2012, shows the very record low extent of Arctic ice cover at the very end of the warm season, which is mid-September. And it's compared here in the image to the 30-year average cover shown by the yellow line. In September 2009, commercial maritime transport began through the Arctic Ocean via the northeastern or northern route along the coast of Russia, when 2 German bulk carriers transited the Arctic Ocean. But they were careful. They had contracted Russian nuclear icebreakers to closely watch their transit. Such type of transit through the ocean, Arctic Ocean, will become common in years to come as the ice continues to recede. Maritime transport through the Arctic shortens the transit from China, Japan, and Korea by 40% to either Europe or the eastern seaboard of the North America, and therefore have great savings in both time and cost. The potential environmental effect of warming climates in the Arctic will have far-ranging impacts on resource exploitation. This in turn will have a tremendous impact on human livelihoods, animals living in the Arctic such as polar bears, loss of habitat, thawing of the tundra with the release of more methane, and the risk for environmental destruction as Arctic infrastructure increases. The very tragic collision on the 15th of April 2012 between the Titanic on its maiden journey and an iceberg in the North Atlantic Ocean 600 kilometers to the southeast of St. John's, Newfoundland, caused the death of 1,500 persons and gave rise at the same time to the first global convention, SOLAS, Saving a Life at Sea, by the organization which was to become the International Maritime Organization in the 1970s. Much advance has taken place during the 100 years since the tragic sinking of the Titanic. Still, 100 years later today, in spite of superior technological advances in maritime navigation and communication systems, the Costa Concordia scraped the rock within 100 meters from shore of an island in the Mediterranean, listed to one side and sank within hours in shallow water, costing some 33 persons their lives. Neither the Titanic nor the Costa Concordia accident should have happened. Both accidents can be attributed to human errors. With 90% of the global trade transported by ships and 20 million cruise ship passengers, creating a sustained $40 billion annual business, serious maritime accidents occur far too frequently. The 2010 Deepwater Horizon accident, an oil spill, was a result of a blowout of the Macondo well at a depth of 1,600 meters in the northern Gulf of Mexico of Louisiana. The oil spill flowed unabated for 3 months. It's the largest accidental marine oil spill ever. Fortunately, the explosion killed 11 persons on board the platform and severely injured another 17. The oil spill was, the blowout was eventually capped. It took 3 months to cap it, but during that time it managed to release 5 million barrels or 800,000 cubic meters of crude oil. Likewise, this accident should never have happened and was due to the series of human errors. Human errors in the maritime world are far too frequent and often have unfortunate consequences in loss of life on ships and also in environmental costs. Maritime accidents occur daily somewhere, from the well-publicized ship accidents to ferry sinkings like yesterday in Hong Kong Harbor, ship collisions, collisions with bridges, and spills of various kinds. In almost every case, these accidents are due to human errors. What's needed is a realistic risk assessment, detailed attention to protocol and process, rigorous training, frequent recertification, solid, relevant education, a reduction of operational stress and working hours, something which has been addressed by the International Labour Organization in the Maritime Convention, which just a few weeks ago was ratified and will significantly help human errors, we hope. Whereas there is nothing that could have been done to stop the 2011 Tohoku earthquake of Japan and the ensuing tsunami. There is certainly very much that could have been done with proper advanced planning to avert the loss of life, property destruction, and the long-term threat to the now shut down nuclear reactors. Planning and recognizing the high-risk threats from earthquakes and tsunamis in locations around the globe could have and should have been applied to save lives and property. The tsunami impact could totally have been averted by advanced planning. But this, of course, would have come at a very high potential political and economic cost and would have had to be going on for a long time. So the question is, what can we do about all these things? Individuals can do very little, in fact, to reduce ocean change. Rather, action is required by governments with a long-term focus and commitment to stop or to mitigate change. The decades needs to be on decades or centuries, and of course with governments typically being in place for 4 or 5 years at the time, ocean and coastal change. Although we recognize that we are still arguing about the rates and the absolute values in this change. It's also very necessary to understand that or model correctly all processes. The complex feedback loops and the nonlinear inherent processes makes this very difficult. Thus, we must not be surprised when change happens sometimes at a rate far faster than we anticipate at the present, or even as a sudden change of state. The rapid disappearance of Arctic ice might in fact just be one such case. Ultimately, changes to our oceans and coastal environments are a consequence of human overpopulation, as well as a very rapid population growth in the past 200 years. We all, as inhabitants of the globe, have a social corporate responsibility to treat with respect the blue earth for the benefit of those who come after us. Thank you very much.